Thank you all for joining us today. We are excited to be continuing our technical information session as we'll be covering what has been and is still a hot topic today, topology optimization and more broadly, generative design. My name is John Graham. I'm marketing manager here at nTopology. And I'm going to walk you through a little bit of the background of the company and talk about some concepts like fields and implicit modeling. And after that, we've really saved the best for which Trevor and Jonathan will cover. Trevor's going to be talking about topology optimization and generative design. He is our director of simulation. And then Jonathan, our lead application engineer, will give some examples and walk through a demonstration of the software. All right, so a little bit about nTopology if you're not familiar with our company. We've been around for several years now, since 2015, and we're passionate about transforming engineering processes that capitalize on the power of advanced manufacturing techniques, which includes additive manufacturing. Now, contrary to what the name nTopology might conjure up in your mind, we're not strictly a topology optimization company. The name nTopology stems from any topology, which most certainly ties into what I said a moment ago about capitalizing on additive manufacturing and the ability to create unique designs, but it also ties into our mission. And our mission has to do with helping engineers better define, represent, and lock down various engineering processes digitally so they can create the best parts possible in the shortest amount of time. Now, all of those things are important, no matter what sort of product you're talking about. But I would argue that in light of the rise of additive manufacturing and all the new ways to define and make a given product, understanding the engineering process is paramount. It's so important. So one way that we help engineers and we enable them to design better products faster, this ties into our vision. We combine elements of design, engineering simulation, and advanced manufacturing in a digital process that makes engineering knowledge reconfigurable and reusable by other engineers in an organization. Look, the easiest way to summarize what I just said there and put it succinctly would be the smarter and more efficient use of data that's driven by physics. Okay, so that's a high-level view of who we are, our mission, our vision, what we've set out to do. So in regards to some of our products, nTopology is best known for creating nTop elements. Many of you have heard of that before. It's a great point solution that's been out for a while. It enables engineers to easily create optimized lattice structures for additive manufacturing. From there, what we did is took our learned knowledge and expanded our scope quite a bit to create this next generation tool called nTopology Platform, or nTop Platform for short. Jonathan's going to show you this in a few moments in a little more detail as it relates to topology optimization concepts, but know that nTopology has the larger vision for an engineering environment integrating, as I said before, design, simulation, and advanced manufacturing processes. That's what platform is all about. And topology optimization is really just an element of that process and that journey. And Trevor will talk more about that. So real quickly, just a couple things to talk about as it relates to platform and some of the benefits and characteristics of it. Performing more design of experiments, design iterations, trade studies, those are all crucial for breeding innovation and designing tomorrow's products. So giving engineers tools to experiment, try out new ideas. This is what platform enables. Being able to explore more models in greater detail and create designs that were otherwise not possible before. So manufacturing techniques have improved, but design tools have lagged behind a little bit in recent years. Well, that's changing now with the advent of things like platform. The third would be collaboration or connected engineering systems. So platform is the only design solution that will allow engineers to simultaneously consider the function, geometry, simulation results, and manufacturing within this computational framework. And then finally, another benefit and characteristic would be the capturing of engineering workflows. So by using this novel concept of engineering notebooks and computational modeling technology, it's going to deliver this highly specific control over advanced mechanical design. And this helps teams document and reuse shared knowledge and proven workflows in an automated sort of way. All right, now let's talk more about this concept of implicit modeling technology and how it plays a critical part in the backbone behind nTop Platform. Implicit modeling, it's interesting. It's a very simple yet difficult concept to get your arms around at times, but it's essentially modeling and representing geometry via math equations, and most importantly, distance fields, or looking at distances from mathematical equations. One thing that's contrary to explicit modeling, if you will, or precise modeling such as BREP or STLs, is it's only rendering and calculating on an as-needed basis, or as I like to say, a just-in-time basis. And so there's several advantages and reasons for implicit modeling, this technology that we've embraced in this geometry kernel we've built from the ground up. One is that since modeling operations are based on distance fields and finding a collection of maybe equidistant points from an equation, since doing that is a very simple operation, modeling operations never fail inside Platform. They're extremely robust. And so this ties into, it's one reason why complex geometry operations are actually quite simple in Platform. And Jonathan will show you some of that later, as he may show you like a shell of a model he creates. The third, since operations don't fail and are computed so quickly, this makes the automating of trivial or mundane tasks significantly easier and more reliable than ever. And finally, the file sizes are significantly smaller than other file types. Because this is equation-based, scalability is significant too. Heavy details aren't dragged along for the ride. Now, I'm really not doing implicit modeling justice by talking about it here for 2 minutes. If you're at all curious to learn more about this concept and what it does, please go visit our website and look at our blogs. We have a series of blogs that we have put out, and I think just today we put out the 5th one explaining in some more technical details and benefits what implicit modeling is all about. So I encourage you to go to that, go to our site and look at the topics. If you click on implicit, you'll find all of them right there. Now, looking at the next page, here's an example of what I'm talking about when I mentioned that file sizes are significantly smaller. You can see the progression there as you go to the right and get to what we call a continuous volumetric expression of a model, where it's really the file size is only storing the equations necessary to render this and query points throughout and find distance fields. It's significantly smaller and the operations are a lot faster. All right, so next slide. If the implicit modeling technology is the backbone that allows geometry representation in this robust way, then fields or distance fields are this unifying language that enables what I would call a true integrated relationship between shape simulation and manufacturing process data. Now, when we talk about fields, we're saying numbers, scalar values, or this collection of data that represents something in space, such as distances, forces, velocities, or in the case of topology optimization, local stress values or stiffness information. One of the primary benefits, and there's many of them, why we use fields, but one of them is collaboration. This is so important when today there exists so many fragmented workflows and point solutions out there. Using the language of fields, different stakeholders can input data as needed to describe a design or a particular process for which is important. And the second I would say is automation. So when geometric operations don't fail, when they're robust because of this technology and the use of fields, this allows for the use of field data to drive operations that were once manual and are error prone. So we have coined this term called field-driven design, and we'll have many more of these information sessions to unpack what this means, applications for which it helps, and the benefits around it. It's such a novel approach to quickly generating, defining, locking down, and controlling manufacture-ready models. All right, so with that in mind, I'm going to turn things over to Trevor. He's going to delve into topology optimization in the context of what I just described, fields and implicit modeling. Trevor?
Thanks, John. Hello, everyone. Excited to be here today. I think kind of jumping off where kind of John left off, I think it's important to kind of set the stage for what we're going to cover today. And so really what we'd like to do is talk about topology optimization, yes, but also in the context of what some of the core things that we work on here at nTopology. So John mentioned implicit modeling, field-driven design, automation, collaboration. Those are really the things that are the primary focus of a lot of what we do. And so today is about how does topology fit into that, and what are some things that some nice connection points between topology optimization and some of our core approaches. So first thing here on this slide, there's a couple terms that I think generally get used quite a bit, sometimes interchangeably. One is generative design. And so there's, some more concrete definitions floating out there. I'm not going to try and, kind of make our own, but generally speaking, we think of generative as the larger computational process that you can put together by an engineer and then use that to generate many designs. And so you could do that by parameter sweeps, design of experiments, but it's really all about that larger computational process. And so in that setting, we think of topology optimization as one of the many tools in the generative design toolbox. It may be a very important tool, it may be the bulk of it, but it's more or less one function call in a larger overall process. And so really today is about how does that kind of look in the software, and how does that all come together. And so a few key concepts that we'll kind of touch on in the next few slides. One is, of course, fields, and what are the connection points between topology optimization, fields, and how it fits into the software. The second one is something we've put a lot of attention towards in automated geometry reconstruction. So we'll touch on that. And I think it's just a general note, it's important to point out that topology optimization, it's been around for a while, but it's definitely kind of going through a renaissance with advanced manufacturing and more computational power. But it's a very rapid moving technology, and so at least being aware of that and kind of architecting a system that you can always be able to keep up to date with the latest and greatest is something we've put a lot of thought into. So just as a concept to talk about, so we've talked a lot about fields, and so how does that relate to topology optimization? So what has been implemented in the software as of today is what you could call your traditional density-based topology optimization. And so at the end of that process, the most basic results of that are, let's say, your mesh and the resulting element densities that were determined by the optimization process. And so that usually is, depending on what your workflow is or what tools you're using, you may have that basic result, and then from there it may be, you may go straight to geometry reconstruction, but there's other things you can do with that if you so choose. And so in our system, we have this very field-centric view, and so at the most basic level, what the output of topology optimization can be thought of just a density field, right? It's just a spatially varying attribute where the element densities are the attribute, and they indicate, generally where does material need to go to, minimize some objective function subject to a variety of constraints. And so the key takeaway here is that this density field is kind of the most basic output, and it's actually a native type in the system. So there's some really nice connection points there and some things you can do with that if it makes sense in your workflow. So being able to modulate geometry directly. I know there's been some other webinars where we saw stress fields driving lattice parameters, and so in theory you could do the same thing with a topology optimization result. The last bullet point is probably a topic for a different webinar, but this idea of connecting this field-driven design of topology optimization to kind of mesoscale material design is something we're working on, and it's kind of the key underlying idea to that approach. This example here is just kind of driving home this idea. So if you think of topology optimization and the density field that comes out of it, just on a basic part like shown here on the screen, you start with that image, your kind of thresholded element densities there, and the picture there on the right is showing just the original part, but in this case, just as a demonstration, we shelled it and filled it with a lattice structure. And so because fields are such a native type in the system, You can extract that directly from the topology optimization, and if it made sense in your application, you could use that field to modulate geometry directly. So in this case, where the element densities are higher, the lattice is a little bit thicker, and then it will thin out as the element densities get a little bit less. And so just as a geometry demonstration to show how that may work, almost any parameter in the software can potentially be a field. So as you find new ways to leverage this type of representation in the system, you can do some pretty creative things with it. This next slide here, kind of how does topology optimization and implicit geometry connect? And so when we first looked at topology optimization and started asking, how does it fit in the system, how best to do it, and we kind of looked at the end-to-end process of how it is really done in practice. We obviously automation is a key part of what we're trying to do in the platform. And when we looked at the kind of the end-to-end topology optimization process, we always saw that the geometry reconstruction is kind of the bottleneck in the workflow. There wasn't that kind of seemed like one hurdle that we would need to overcome to make this to make topology optimization as streamlined and as automated as we'd like it to be, as other parts of the system are. And so really what the enabling capability was, or the enabling technology, was the implicit modeling kernel. And so what we can do with that is take the topology optimization results, or the thresholded elements, and with only a few inputs, we can very quickly and robustly and in a very repeatable fashion get to a smooth implicit representation. And so the picture on the right there, you can see kind of the raw topology optimization results at a selected element threshold. In the middle there's essentially just a function call that will smooth those results into a something that is more like a manufacturable shape. And then the key thing is, not only does it come out smooth, but it is the output is also our native implicit geometry format. And so what you can do with that is, directly from those smooth results, you can immediately feed that down to downstream operations, whether it's adding additional geometric features, maybe rerunning it through an analysis for verification. Anything that you can do with implicit geometry in our system, that's the format you get out of that at this step, and you can continue on with the process. And so this is where we really put a lot of our effort up front, and to us was kind of the big thing that we needed to make sure we had a solution for as we kind of rolled this technology out. And so at the end of that, this is kind of the key step that really enables a connected end-to-end pipeline. So you may have operations that come before this, you may have a lot of operations that come after this, but at the end of the day, it's all connected. As things change upstream, that's going to be captured in your workflow, and when it gets down to the topology optimization, it's going to call it, run it, and then come back and continue on with whatever you build after that. And so that's kind of how we approached it, and how we fit it into the system. And so really it's a technology that the company or the entire piece of software isn't built around, but it definitely we think fits in there quite nicely, and we're excited to continue development in this part of the software. So I think at this point, Jonathan's going to take over for a quick demonstration.
Great, thank you, Trevor. Here's this bracket that Trevor has been describing in the software. So as he mentioned, topology optimization is but one button in our nTop platform, but it is quite a useful one, and so I'm going to walk you through how that looks. So what we have here is a topology optimized bracket, which we started off with a design space like this, with some fasteners down here and some combined loads pulling on these regions here. We can get to a tet mesh of some refined element densities. Now, up to this point, this is topology optimization as many of you have seen or used before, but as you know, now comes the manual labor. And what we don't want to see is engineers wasting their time clicking along a surface like this or having to manually remodel bits after they get this nice organic-like design. Since what you see here is both a TET mesh but also a mathematical field in our software, what we can do is just immediately fit a smooth geometry type to that. And so obviously this is not what we're proposing as the final part, but the ability to instantly Boolean back in features allows you to put back in those passive regions right away. So something like this, you could then do post-modeling operations on, as Trevor was describing, because it is simply a native geometry format in our software. So if you wanted to maybe put a lattice region in, or, which I find quite exciting, if you wanted to shell the entire part in one click, you can also do that. So if you're using topology optimization as more of a load path guidance approach and you wanted to shell this for some other reason, then you could certainly do that. And so you can see a complex geometry like this is instantly shellable. And the way we do this is, I mean, it's really just the implicit format showing its strength here. You could shell anything from this bracket to a lattice of 1 million unit cells and have hollow tubes instantly. It's quite a powerful concept. So let me show you this close up a bit here. Okay. So if we rewind a bit, we can start off with our design region here. So what we had in this topology optimization was a load case with some constraints, as I showed before. And the loads are pulling on it this way. What we end up with, as you'd expect, would be transitioning through this. So if we get to some threshold, what I showed you earlier was one threshold. What I want to show you now is that, hey, if you have a design change, that's no problem. Remember, there's no manual effort involved here. We can make a change. Let's say we take a more conservative approach in our topology optimization and say change this. Or actually, let's say we take a little more weight out of it and change the threshold just a touch. So this is going to rebuild that entire part. And so that is running now. And we're just rendering that view. So I've taken, in this case, intentionally a little bit more weight out of it than one might want, and we lose a bit of density there. But that's no problem, because remember, as this is a native geometry format, putting in some extra material where needed or modifying a member, that's really easy. So I already had this cylinder placed here, but what I'm going to do is then union that directly to my part here. So I'm just going to drag and drop these. You can also type them in like this, and I'll give it a bit of rounding so that it's nice and smooth. So that's rendering there. And now you can see that we have this nice reinforced region as opposed to that. So that's an instant modeling operation, and we're still in our native format. Now, once we have this, I mean, we can mesh it for manufacturing. We can mesh it for with a volumetric mesh for post-validation. But what I always prefer to do is just slice it directly for additive manufacturing. So we can slice our implicit models. That would look something like this. So I'll just do a rather coarse spacing just so we can actually see the slices. So here we go. So So you could then export these to a variety of machines today, and we're growing that list rather rapidly. Okay, so that's just a quick demo of topology optimization in the software. We actually had this part built. This is fresh off the press from Volunteer Aerospace. We got 2 of these built, and we're just cleaning them up now, and we'll be showing them at Rapid at our booth, so be sure to stop by for that. At this point, I will hand it over to John to conclude this webinar. Thank you.
Jonathan, Trevor, thank you very much. Very interesting stuff to show. Guys, before we get into question and answer, which there are many great questions I can see coming in, just want to draw your attention to a few things. If anything you saw today you find intriguing and you want to inquire a bit more, shoot us an email, sales@ntopology.com. Alternatively, go anywhere on our website, click the Contact Us button, and fill out a form. We'll be happy to get in touch with you, give you a personalized demonstration, or do whatever we can to take the next step to see how the software fits your application. Also, I mentioned our blog earlier. We've been much more aggressive in being thought leaders and talking about this technology, not just promoting our software, but encourage you to follow our blog. We will have a sign up in the very near future, so you'll be informed as blog posts come out in real time. Future information sessions such as this, you will see them on our webpage under the resources section and probably somewhere in a large banner. So please do sign up for these. We would love to see all of you here again. And then finally, 2 weeks from today, right now, we will be at 2 very prominent shows throughout North America. Rapid in the Detroit area and Space Tech Expo in Southern California. If you're in either of those areas, we would love to see you. Please stop out and come visit us. We will have many, many real applications, real parts on display. Jonathan just mentioned and showed one a moment ago. So please stop out. We'd love to have a conversation with you. And that's about it for announcements. I want to turn it over to questions now. So several have been coming in, like I mentioned. Trevor and Jonathan, I'll throw a couple out to you. If you want to take a few on your own, feel free to do that. You know, one question I'll throw out. Someone asked a great question about importing files, and if they could take the topology optimized results, maybe an STL file from another system, and bring that into nTopology. What would we be able to do from there?
Yeah, that's a great question, and something that's come up a number of times. So yes, we can definitely do that. I mean, the topology optimization results that are generated in our software are very similar in terms of the way they're represented in terms of data. So yeah, we could definitely bring in external topology optimization results, or maybe a mesh from those results, and run the smoothing process, convert it into implicit, and then do all the downstream work in here. So that's definitely a possibility.
All right, great. Thanks. If there's any questions you guys want to tackle, feel free to do so.
Let's see. There's a question about analysis times beyond linear static and multiple load cases. I think roadmap wise, you know, like I said early on, we definitely put a lot of effort so far into the converting results back into implicit and the smoothing work. We have the kind of the basic linear static implementation. We're working on modal, multiple load cases definitely. So we're definitely building out. We've kind of built the core, and we're scaling up from there. And a lot of that's going to be customer driven. A lot of I'd say the most successful topology optimization applications I've seen are ones that are really kind of finely tuned for a particular application or set of physics. So as we hone in on those things, we'll definitely be scaling that up.
Jonathan, here's one for you. Let me see if I can paraphrase. You imported in your demonstration, you imported that cylinder, merged it to the other body, and put a round on it. Is that possible to do with really any geometry you bring in or other file types?
Yeah, so the Booleaning Booleaning in a feature like that is pretty universal. So in that case, I just put a little reinforcing strut there. We've actually, just to build off of the first question, we've had use cases where people bring in a big clunky STL file just to do some Boolean operations on it in implicit world, and then blast it out as slices for manufacturing. So doing those operations is really, you can do them with any format that you bring in, as long as once they're in implicit format, which we convert to pretty much instantly, you're good to go.
All right, great, thank you. We are running close to the end of our time. Any other questions you guys want to tackle?
There's one on is a smoothing first necessary before additional downstream? It's the only absolute requirement is that you convert it into implicit. There is a kind of a generalized function call in the software to smoothen that implicit. So it's not required, but of course it depending on your the mesh size, your topology optimization, you could get element or I guess a boundary mesh that generally you may want to smooth it, but technically it's not required, but it is generally useful.
All right, thanks, Trevor. One more that just came in. Trevor, maybe if you want to handle this. The question was about the roadmap for the future. What kind of direction is nTopology going with regards to topology optimization?
Mm-hmm. Yeah, we kind of touched on that earlier in one of those questions, but a lot of it, it's a very customer-driven, I'd say, development plan. I mean, a lot of, when it comes to capturing every practical constraint, engineering constraint in topology optimization, it's definitely a lot to bite off. And so things that we think are the most useful will get prioritized. It does, as I alluded to in some of the slides, there are some things that we're building out that are more geared towards connecting topology optimization to support kind of lattice design. And so that's an interesting way to merge those two concepts together that we're building out as well. So that's kind of where we're heading.
All right, great. Thank you for that. Folks, I think we're about out of time. Thank you all again for coming. We sure appreciate it, and we hope to see you on further information sessions as this. Have a great day.